Hello, welcome back to the channel. Let's solve another challenge today. Today's problem is the lowest common ancestor of a binary tree, 3. So this is a very common interview question, a technical interview question. So let's see what we are given. So we are given two nodes of a binary tree, P and Q, and we need to return lowest common ancestor or LCA of these two nodes. Interestingly, we are not given the root of a tree. So instead, we are given that each node will have a reference to its parent node. The definition of for node is given below. According to the definition of LCA, the lowest common ancestor or LCA of two nodes P and Q in a tree T is the lowest node that has both P and Q as descendants. And we can also let that the node can be the descendant of itself. So let's see. These are the examples. We can see the number of nodes in the tree is in the range from 2 to 10 power 5, and the values of the nodes are minus 10 power 9 to 10 power 9, and all values are unique, and the two nodes are not equal to each other, and P and Q are guaranteed they exist in the tree. As you can see, this problem is very common, and they are asked by major companies during the interview. So let's look at the problem. So these are the nodes. Let's see what we are given. We are given the tree, and we are given the nodes of a tree, and we are given only two nodes. This is a root, but we are not given the root. So what does LCA mean in the first place? LCA is basically is the lowest node or the furthest node from the root and the tree that has both nodes and the tree as descendants. For example, LCA of 5, 5, and 1. This is a 5 and 1. What is the lowest node? It is 3, right? And what is the LCA of 6 and 4? So the parent of 4 is 2, and parent of 6 is 5. Parent of 2 is 5. So the lowest node in the tree that 6 and 4 as a descendant is 5. So we need to return 5. So we have already solved the first variation where we are given the root of a tree and we are given two nodes, and we need to determine what is the lowest common ancestor of this two node. So we are given what are the key points. So instead of giving the root of a tree, we are given the parent pointer to the parent, right? Each node can tell us who its parents and how it can help. So we can climb up to the root from the given reference to the parent, and we don't need direct access to the root, right? And number two is no root is needed. We don't need the root. And in other variation of LCA problem, we are given the root and we are required to have an access to the root, right? And so in this problem, we can solve this problem from bottom up. So we start from the node and we climb up the tree to the root, right? So then we need to find what is the lowest common ancestor of a tree. So there are two ways we can solve this problem. One is it's basically one algorithm to get the lowest common ancestor of the two nodes, or we need to build the path from each node back to the root, right? And the number two is get two lists of nodes, path P and path Q, and we need to compare this list from the end. Let's see the example here. Let's say that if we are given the 6 and 4. What is the path P to the root? So 6 and 5 and 3. 6, 5, and 3. If we construct the list, so basically 6, 5, and 3. And the path Q, we need to go climb up to the tree. So basically it goes to the 2, and from 2 it goes to the 5, and it goes to the 3. So 4, 2, 5, and 3. So this is a list. So then what we need to do, we need to loop this root from the back. Okay, this is a 3 and 3. So they match, right? Because this is a root. What's the next node that they match? The 5. And after that, 6 and 2, they don't match. So we need to return the closest, the last node that they have in common. So instead of typing, so I have given the code here. So initially what we need to do, we need to write function get path to root, and we need to initialize empty list and while node exists, and we need to add the node to the path, and we need to update the node to its parent, right? Because we need to go climb up the tree. Then while node at the end, once we reach the root of a tree, the next node will be none, right? Then we need to return the path. So this is a helper function. Then our main function will be here. So we are given the two nodes P and Q. So we need to build the path P, right, by passing this parameter, and we need to build the path Q by passing the Q parameter. Then we need to get the length of each path. Because we are returning as a list, right? I and j. Then there's the length pass -1 and length pass minus q minus 1. Then we need to do this while loop while this length is bigger than 0 of p path, and the q path j is also bigger than 0. Then we need to say they are equal. So we need to just keep looping until they are not equal. Once they are not equal, right, then we need to decrement this the I and j. Then once they are not equal, so it will be returning the last node that they are equal, right? So this is the first approach. Basically, the approach is we construct the path from each node up to the root. Then we loop. We start comparing from the very back of the two lists, and we need to return the node that they are not equal, right? The last node. So this is the first approach, and the time complexities of h is the height of a tree, and space complexity is the same, O of h, right? So if we don't have any problem with the space, so we should be okay with this algorithm, right? But just in case if we have a limited space for very large trees, right? Then we have there is another algorithm we can look at this. So algorithm 2. So this approach is two-pointer approach. What happens in this approach? So we need to set 2 pointers. The first pointer we're going to set to P, and the second pointer we're going to set to Q. Then we need to climb up the tree for each node. When pointer 1 reaches none, imagine if this is 6. From 6 we need to go to 5. Then we need to go to 3. Then after 3 it will be none, right? Or null. And after it reaches the none, then we need to set the pointer 1 back to Q. This is, let's say this is a P, this is a Q. After we reach from pointer 1 to none, then we are going to set pointer 1 to Q. The same thing we do for pointer for pointer 2. We climb up the tree 2, then 5, then 3, then after 3, then it will be again none. After pointer 2 reaches none, then we are going to set this pointer 1, and we are going to set pointer 2 to P, the first node, right? Then we just keep repeating this process. So we climb up the tree. When pointer 1 reaches none, we set this to Q. Then we keep repeating this process for pointer 1 and pointer 2. After 1 or 2 iteration, then they will be meeting at one point, right? So once this pointer 1 and pointer 2 converge, 2 pointers, they converge, and we need to return that node where they converge. For example, let's look at the dry run. So the pointer 1 is 5, pointer 2, and now in the first node is 5, P node, and Q node is 1, which is very up, right? And pass of P. So where is that? First we go to 5, from 5 to 3. Then after 3, it goes to none. After it goes to none, then what's Q pointer is 1. So we're going to set to 1. Then we do this for the Q1, right? So from 1 to 3, after 3, it's none. Then we set to P. Then from P, then we just go up again, just 3. So at 3, they are meeting. So this 2 path, they are converging. So basically, we need to return this node in the tree. We can do the same again. So basically, we can just look at 6 and let's say 4, right? From 6 to 5 and 3 and none, then we set to 4, this 6. So we can just write from 6 it goes to so from 6 it goes to 5, then 3, then none, then 4 to 5, right? From 4 it goes to 4 to 5, 3, none, then 6, 5. So they are meeting at 5. So they are converging in one node, right? So we need to return 5. So basically, also if we look at here, so we can see the LCA of 6 and 4 is 5. So we are going to return this 5. So let's look at the code. So this is very simple code. So we are going to iterate pointer 1, set pointer 1 and pointer 2 to P and Q. And while pointer 1 is not equal to pointer 2, and pointer 1, we need to climb up the tree. So pointer 1, we're going to set to pointer 1 dot parent if pointer 1 dot parent, if the parent of a pointer 1 or the P node exists. If it does not exist, it means like we are at the root, right? Or above the root. Then we are going to set this to Q. And the same thing we are going to repeat. Pointer 2 is pointer to parent if pointer to parent exists. Else we are going to set to P. So at the end, once both pointers they converge, we are going to return LCA. Either we can return pointer 1 or pointer 2. So they are the same thing, right? So in the time complexity, because we are going through from a node up to the root, so that's basically of h. H is the height of the tree, and space complexity is O of 1 because we are not really taking in a space. We're not building in a list or dictionary. So this is these are the two approaches of this problem, and 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 this problem is a very common problem that are asked in the interview settings. And please subscribe to the channel and ask questions and comments if you have any questions. And I'll see you guys in the next sessions, next videos.